Hey everybody, this is Alan, and really apologize for not being there today, but I have had some family difficulties that I'm having to take care of. But I did really want to share this particular these concepts with you here as a video, and hope that this is a good predicate to understanding where we're going. You know, the idea is that today we're kind of seeing all these disciplinary silos collapsing: land, engineering, geology, geophysics, and what have you. And really they're kind of collapsing towards a robust and rich Earth model. And this is kind of the natural convergence point for nearly every kind of analytics that we're going to go do. So what does this mean by kind of consolidated earth sciences? And you know, the ideas are that we're going to be describing the geology numerically, which is structuring data. So think about what the digital age brought forth with regards to geophysics. It was unbelievable. I mean, we went from looking at wiggle traces on paper and measuring them to being able to extract all sorts of information from the pre-stack and the post-stack and what have you. And geology ended up just kind of being the same thing that we did on the paper basis, just we're just kind of doing it digitally. But there's as much out of the geological information, geological framework that we can extract as we did in the geophysical framework. And so, you know, the whole concept of how do you take the very best of all worlds? You know, in seismic data you have, you know, good sampling in terms of 3D, in terms of horizontal sampling, and then vertical sampling. We have incredible sampling with regards to to the well logs that we have. And so let's just take the best of all worlds. The idea also is let machines do the rote work, you know, and this is what we'll talk about in terms of artificial intelligence and machine learning. We'll spend our time thinking and testing various ideas instead of doing the rote work, which is really analyzing. And this is to be able to test a lot of scenarios, to be able to look at these and look at things in terms of probabilities, which is the next thing. And if you can put yourself in the mindset of looking at things as probabilities, it opens up a whole new world of being able to quantify and view the world, and break shackles from seismic resolution to log resolution, as we talked about. And then using seismic data as a soft guide to inform our Earth models that are there at the well log resolution. And how do we do it here at Drilling Info? We spend a lot of money in terms of cloud technology, you know, R&D, which is a lot of you guys integrate with through the Drilling Info website, and some of you are starting to see with regards to being able to integrate with your own data as applications behind your website, behind your firewalls in some ways, with regards to our larger clients with their own data stores. And then kind of what we do on the geology, geophysics, and engineering R&D, we do on the DI Transform application, and we use this with regards to our internal groups. And we have 200 plus highly technical client users that get the first view of a lot of the things that we're doing in terms of R&D. So, you know, I'm just going to give you an example here of what it means turning pictures into data, kind of structuring data. And this is just something that we have, this is some technology we've developed to be able to go more quickly use neural networks and what have you, to be able to go out there and digitize seismic data using some fairly novel, well log data, using some novel methodologies here. So, you know, and the idea being that what we're trying to do is we're trying to extract these numbers. You know, the shapes and the pictures are not good enough. We need to have the numbers. And so, you know, as you can see what's happening here, it's just being able to go out there and extract these numbers in a big way. And then another methodology of structuring data is what we call wellbore geometrics. And in this case right over here, these are just the tops And then here are the different wellbore geometries in here, and this is something we spend a lot of time doing, is digitizing these wellbores, looking at the tortuosity within those, looking at the landing zones, looking at actually the subbenches within the landing zones, and really looking at the details of the geology and really the petrophysics of the rocks in which they're landing. And as you can see, even in some of these right over here, there's several different, even in a particular landing zone like a Wolfcamp A or what have you, there are several places that they play, you know, basal, upper, what have you, with regards to doing that. And then figuring out different ways of basically creating scalars to understand, you know, what they are. In this case right over here, we're looking at Dean Lime, and we just picked a certain wells that are in the Dean Lime, looking at particular wells over here. This case, it was not completely contained in the Dean Lime, went into the Sprayberry. And then, you know, and also just looking at heel to toe links, toe ups, toe downs, porpoising, tortuosity, and really what these are, you know, porpoise counts, all sorts of different scalars with regards to being able to determine, you know, what is, you know, what are important in here, because you need to be able to go out there and look at all these things and then go out there and understand whether these actually help or hinder your production. And in this case, we're just putting it between markers, but I'm going to show you some pretty cool stuff in just a moment. And as you can see right over here, it's just all sorts of different statistics with regards to being able to take a look at these and essentially filter these so that you can use these in real analytics. By the way, we do this all the time. So not only do we have the tools to go do this, we do this. We deliver all these pieces of information already done, and the tools necessary to be able to go look at the data and to be able to do your own. So I think we believe in ultimate flexibility. Here's another thing. This is machine learning and artificial intelligence, and this is from a methodology that we developed a couple of years ago that we patented. It's automatic well log tops picking. And what's really interesting about it is because it does allow kind of some it is machine learning and artificial intelligence, and as you start to constrain the answers, they get smarter and smarter with regards to doing this. And so in this case right over here, you see a gamma ray section that is, you can see the major packages, but then as you basically get the major packages figured out, you'll start to notice some really, really finely detailed kind of sequences within, you know, kind of third, fourth, fifth, sixth, you know, order sequences within that become very apparent, that are not apparent typically as you're going out and doing these things. And so in this case right over here, you know, the beautiful part about this is we've done this. We've gone out there and you know, carefully picked the tops, picked these seeds, and then extrapolated over to hundreds of thousands of wells, so that you can, anytime you bring in wells or what have you, it nearly is just automatic. It becomes automatic interpretation. And then you have these other concepts right over here. So, you know, for instance, as we map out all these particular areas over here, we have, in this case right over here, we're using 5 different wells. We use an unsupervised classification just in our system. And it's a k-means classification, and it goes out there and says, if we decided that we think this can break up into 4 lithologies, you know, here is the classification of those lithologies based off of these 5 well components. And then here is the proportions of those 4 lithologies, because there's never a perfect, you know, kind of fit in here, but there's proportional aspects with regards to that. And then as you come over here to the next step, this is the concept of looking at it as a unsupervised, and then coming in here and saying, well, we know from a petrophysical point of view that here is sands, here is shales, or what have you, and then that becomes a supervised classification, and start to look to see how much the automatic methodology compares to the supervised classifications that you have. And then also going out here and really understanding which kind of signatures do you need to have in order to be able to go identify these particular lithologies out here. In this case, right over here, we use 3 of the wells, or three of the measurements, 3 of the logs, and you can see we still have 90 something percent correlations with 3 of the 4 different methodologies, and one of the different this tan facies that you see kind of as a minor facies within here is really the only one that is suspect. But at least we know that whenever we see that, it's suspect. And then this is really exciting. This is something that we've just kind of created. It was, thinking of the subsurface as 3D Earth models, reservoir models, and this becoming the framework of how we go out and do these things, but we do it at very high resolution. The idea being, this is what you would typically think of in terms of voxel volumes in the subsurface, and going out and doing this, and we really look at this and saying, kind of well spacing, kind of regularity is interesting, and to be able to go look at this in vertical resolutions, especially with regards to where your well bores may be encountering, is really kind of fascinating. And these concepts of creating these 3-dimensional grids. And the thing that's interesting about these 3-dimensional grids is you come out here, and if you start really looking at this, it comes over here and says, we can you start sampling these, and you have all sorts of kind of depositional environments that start to become apparent. And how can you go out there and quantify that, or how can you allow kind of the computer to help guide these particular things? In this case, right over here, this is an example of this methodology. We're just going to go out and pick pick one of these, go out here and look at the gamma rays, and pick a few tops. And then this is a whole methodology with regards to us calculating what the lithology will be at any particular location that's been undrilled. And in this case, it's a vertical location. But then, as you see these little red zones over here, these become the zones of high of low probabilities. Essentially, how do you go out there and look at the probability cloud around these? And frankly, that methodology is really interesting with regards to looking at depositional environments themselves. In this case right over here, this is just an example of using a structural model in a few of these samples right over here. And to be able to go out there, in that case, when we're talking about downlap or thinning out or what have you, just using a couple of wells to be able to go out there and identify what is actually happening within these zones over here. Is this a truncation? Is this thinning out on top of a structural feature, or what have you? And really starting to just deal with things as geology, kind of dynamic geology in the subsurface. And this is just an extension of that, because at any one of these points that we're going out there and we're calculating it out over here, we could actually go create a pseudo well log in this case the 2-dimensional basis. But just going out there and just saying, let's go out there and create a various pseudo well logs that are our best prediction of what the gamma ray might look like at any one of these positions around there. This is essentially the seismic porosity in terms of soft data. How do we bring seismic into this whole thing? This was seismic porosity. It was an inversion kind of work that we did with regards to looking at seismic porosity and then mapping these to the well bores. And what's really important about that is it allows us to go do some pretty cool things, because here is the seismically derived porosity on the left over here. And then here is essentially my gamma ray, and here's a correlation, calculating out the correlations between these particular zones. So these can help guide, our synthetic gamma rays as we go calculate those away from there. So in this case right over here, let's go build out a horizontal well log. Here is essentially a whole bunch of gamma rays with regards to the three-dimensional surface. Here is the seismic porosity coming through here with regards to that component. And then using the seismic porosity, that map to the gamma rays, to be able to go take a look at what these might be, and using seismic data to help refine what where the geology is that you're really intersecting right over here. So now what you've done is you've used seismic data to put you into very, very fine-grained understanding of the subsurface, at a foot by foot sampling basis. And here you go with regards to being able to go do that. And if you think about that, if we can map it to essentially a wellbore, then we can certainly go out there and create volumes. And in this case, right over here, this is a synthetic gamma ray volume over a sample area we have that has a lot of well control, what have you. But it's a mile by a mile and a half, over 20 million nodes, and it took less than 30 seconds to actually go create this. And you can see some really fascinating detail with regards to the geology and the gamma, lithology in here with regards to what you're doing. So this is pretty exciting to us. And then, of course, the last, taking it to its culminative, kind of the culmination of these things is how do we go out there, bring all these things together, and then be able to go out there and identify what's the most important. We're using this in a multivariant, nonlinear multivariant methodology that we are doing across the board. We're providing these kind of things, but it's going out there and allowing you to also go out there and input your own information so that you can be smarter, a lot smarter than we can be, because you have a lot of particular data that you might have. In this case, right over here, identifying various different, in this case, we have a few things we're looking at with regards to how much they drive in production. And you can see right over here the significance and the sensitivity, and that the seismic porosity is a major driver with regards to initial production, or first-year productions, or what have you, over here. And this is what we kind of suspected coming in here. But if it was, if there was a kind of natural porosity, was that really helping? And in this case, this area of the Permian Basin, they were looking at that and saying yes. And then also looking at all these different various variables on a variable by variable basis, you don't have much kind of linear relationship to this. And in this case, going out here and taking a look at these on a nonlinear basis, matching it all out and creating a model, so that if we have come over here and say we're going to drill a 3,000, 2,800 foot, 2,900 foot lateral, then and we have certain, and we're going to try to stay in these porosity zones, what should we be able to go do? Or at least saying that we have land that allows us to drill a lateral of 2,900 feet within regards to this, with regards to a porosity zone. How much should we be able to go create out of that? And so this is the answer to that, and it's coming up here. I guess it's coming up here in the next one. In this case right over here, then it goes out there and looks at, this is kind of a similar situation we did with the Wolfcamp A, and this was going out here and calculating what would be the cumulative oil if everything was drilled kind of more or less the same, optimized to the region. So this is what we call regionally optimized. If you're going to drill all your wells exactly the same, what would be the one that maximizes your oil production? But the other aspect about it is to go out there and say, well, we're going to honor the geology, and we're going to vary our engineering based off the geology, and that's where we can get to location optimization. And what you can see right over here is it's not a bad correlation. This correlation actually is about a 70% correlation coefficient with regards to predicted 6-month cum versus actual 6-month cum through here, using a few geological parameters and some engineering parameters. As we add more parameters in here and that are important, then what we start seeing is this cloud starting to collapse. The correlation coefficient, the R-squared coefficient, get better. But in this case right over here, it's just saying, here's our what we should get in terms of cum oil. And what's also cool about this is it's really easy to go put the cost. What is the cost differential for adding more proppant? and what would be my return on investment for the first year by going out and doing that. And then coming over here, in this case, just right over here, this is just saying I'll look at it from a linear basis, various nonlinear ways, and if I wanted to look at it in terms of harmonic relationships, we could go look at those as well. But what's interesting right over here is the length. The wellbore length is giving us the highest significance. The isopac of the horizon is giving us, it makes sense, how big is the can. The total proppant is giving us is a high correlation. The GOR, the initial GOR, of course, these all make sense. But also NF, NF is high temperature. There's various different pieces in here that are all contributing to these things, and you can see how much contribution any of these particular things have, and it changes area to area. But this is what our teams are using to actually go do a lot of the looks through here. But this is one of the things we do for consulting. It's one of the things we do with regards to taking you and making you very adept at doing these kinds of analyses. And these are also kind of the scalars that we pull out and things that show up in a variety of different ways in drilling info. So I hope this has been kind of interesting to you, because I think that really what we're doing in drilling info is pretty darn interesting, and I think the way that we filter data to be able to go out there and do a lot of things is pretty fascinating. And again, I'm sorry that I'm not there today, but I look forward to seeing you soon. Thank you very much.